We have finished the background conceptual part of the course, and this middle part deals with all of the actual taxa, all of the actual organisms that we call the dinosaurs. And so you notice I use the word taxa. That's the same root as the word taxonomy, which is how we classify or label all living things, but also all fossil things. So you've probably been exposed to this many times, even since elementary school. And this is the hierarchical system as you see there. Kingdom, phylum, class, order, family, genus, species, going from the largest grouping, kingdom, down to the smallest species, which we talked about last time in the evolution section. Remember, species is the group of all interbreeding organisms. And so those larger groupings include larger sort of baskets in which different taxa are included as part of some generally related group of organisms. And so this simple spreadsheet here has the taxonomic hierarchy on the extreme left side: kingdom, phylum, class, order, family, genus, species. I always learned it as a kid as Kathy poured coffee on Fred's good suit. There it is. And then I've simply put 4 different organisms over here, 2 of which on the extreme right are living organisms that you know, and some of you know very well. So on the extreme right we have the dog, Canis familiaris, and notice it is part of the kingdom Animalia. It is part of the phylum Chordata, which includes all organisms that are vertebrates and a few other weirdos. The class Mammalia, you all have an idea what mammals are. The order Carnivora, which includes dogs and cats and bears, but also skunks and weasels and a few other things. The family Canidae, which includes all doggy type species. The genus Canis, and then familiaris, and this is your family dog. Whatever your breed of dog, husky, malamute, German shepherd, poodle, whatever it happens to be, they're all Canis familiaris. Right next to that, going towards the left, we have Canis lupus, which is the wolf, and notice it is the same kingdom, the same phylum, the same class, the same order, the same family, the same genus. It just differs by species. And the more of these categories that any 2 organisms have in common, the more closely they exist in sort of an evolutionary sense or a relatedness sense. And then go left one more column to an organism that's important for us here, a dinosaur. So dinosaurs were also animals. They were also chordates, but rather than being mammals, they are in a different class than your dog or a wolf. They're in the class Reptilia. And then we have some other names for the order, the family, and then of course this is Tyrannosaurus rex, the famous king of the lizards, the tyrant lizard king. This little group that I have over here, this is just an oddball, just to show you that you can take any animal and put it here. You can take any plant and put it here. They would just be something that differs right at the kingdom level. But this organism in this column here is an animal. It is the phylum Mollusca, which includes clams and snails, octopus, squid, things like that. The class Gastropoda are snails, then a few other things, and then Nerita splendens is a little species of snail that's common in the Caribbean. So this system of naming things, in a rough way, it shows us evolutionary relationships, but it is, in a sense, unreliable. Biologists over the past few decades have discovered more sophisticated ways of telling the evolutionary relatedness of organisms, and they don't really use taxonomy for that. Taxonomy is used for naming things, for putting them in the proper drawer in a museum collection, but doing actual evolutionary relationships, we use something else. And that something else is a science, a discipline, a method that we call cladistics. It's a way of making these tree diagrams. They look like a branching tree that show these evolutionary relationships. And it's based upon what characters organisms have in common rather than what they don't share in common. It's a very complex subject, and if you're really interested in this type of thing, there are a few classes in the biology department that you can take for this. But for us, let's just make this transition. We recognize taxonomy for naming things. We recognize that it has an evolutionary significance, but it has been replaced largely today by this science that's called cladistics. And the cladistic science produces or produces diagrams that we call cladograms. And this diagram here is the cladogram. It's the one that I'm going to refer to again and again and again. It's the major cladogram or evolutionary tree of all of the major dinosaurs that we're going to cover in this class, all the ones that exist really. And everywhere you see a little dot, notice there's a red dot where there's a branching. So you see a dot and then suddenly two lines branch off from it, except for this extreme top row. But every one of these dots is defined by a specific character. So dinosaurs, we recognize what dinosaurs are. I already said that they all have a specific type of ankle. You go up this side here and we reach Ornithischia. Ornithischia is going to be defined by a specific type of hip arrangement of bones. And everything above that dot has that ornithischian hip. Go up a little bit farther, there's a couple other dots, and anywhere you see a dot, usually we've also named it. Every one of these dots, you know, is called a node, and we've named these things, and every one of them is defined by different characters. Now, for living organisms, they're defined by all kinds of things. Their genetic makeup, morphologic characters, behavior, all kinds of things. But for dinosaurs, because they're fossils, every one of these nodes is defined by specific bone or tooth characteristics that are found in them. And again, above the node, everything has that bone characteristic. Below, they do not.